Hello class. Now we are going to study about electromagnetic induction. Okay. So earlier we have studied about Oersted's experiment. So Oersted's experiment try to say that a current carrying wire or conductor always produce a magnetic field around it. Okay. So if there is a current carrying conductor connected with a cell and cell is providing electricity current to the current conductor. So we can find an electric field around the wire. This is called magnetic effect of current. But now we are going to study about how can we find a electric current with the help of magnetic field around it. It is just reverse to the magnetic field of electric current. Okay. So in this incident, an electric field around a conductor and some extra efforts applied by us creates an electricity. So there is a basic difference between both of the things. First is current produce electric field in current produce magnetic field. Sorry for the electric field. Current produce the magnetic field around this conductor, which we call magnetic effect of current. But in this, where we are going to study about the electromagnetic induction, in which magnetic field around the conductor produce electric current, like generator, a turbine we use for supply of electricity or electric current. So after the Oersted's experiment, Michael Faraday think about it first time. Is that possible that the magnetic field around the circuit, around the conductor can give us electric current? Okay. So what did he do? Faraday taken a closed conductor in the form of a coil. He created a closed circuit where a conductor in form of coil is connected with a galvanometer. Galvanometer help us to know about the magnitude of current and the direction of current. Okay, so galvanometer we use as a meter for current and voltmeter for voltage. So just think about this. There is a galvanometer and there is a conductor wire in the form of a coil. Okay, and now there is a bar magnet. This is the south pole and this is the north. So we know about that in every bar magnet magnetic force lines from north to south. We can say that these are the magnetic field lines generating from north pole and entered in the bar magnet from south pole. Okay. So near the poles, the density of magnetic force lines are higher, so that we can say that the density of electric field is higher at the poles, and as we go away from the poles, you will find that density of magnetic field becomes lower and lower. And now then when you approach to the other pole of the bar magnet, the magnetic field become more and more density. So just think about 2 points, point A and point B. Point B is a place where the density of magnetic force lines are low, and point A is the place where density of magnetic field lines are comparatively high. So when we start approaching, when the North Pole starts approaching the coil, you can see that the magnetic field in the coil is changing with respect to time. And a changing magnetic field produce a deflection in galvanometer. So we can say that a changing magnetic field in a coil produce electric current in the coil, and when we stop this movement of the bar magnet, the galvanometer is not going to show any kind of deflection. So the thing is that when we are going to get any deflection in galvanometer, when the bar magnet is moving towards the coil. On the other hand, if you start moving the bar magnet away from the coil, this is the condition number A, condition B, condition C. So from condition B, you are going to attain a new condition where the bar magnet, earlier which was approaching to the coil, now the bar magnet is diverging from the coil and going away from the coil, where you can see that the electric field or electric force lines are comparatively less in amount on the coil. So the magnetic field in coil is going to be lower. First, from case A to case B, the magnetic field in coil is increasing. Now the magnetic field in coil is decreasing. So when you put out the bar magnet, so in this process you will see the magnetic field on the coil is decreasing and you are going to say a new deflection in the galvanometer, where the deflection is just in opposite direction from the previous one. So this incident does not happen only with the north pole of the bar magnet. You will see the same thing is happening when you are doing the same process, keeping the south pole towards the coil and north pole in opposite direction of the coil. So here comes some conclusions. First of all, according to Oersted experiment, where the current produce magnetic field around the conductor. So just think about, if we establish some magnetic field around a conductor, are we going to find any current in conductor? No. Just a conductor, north and south. The magnetic field, in this case, the magnetic field in which the conductor is placed remains constant with respect to time. Means the magnetic field in which the conductor is placed is not changing with the time, and you can't get any kind of current in the magnetic field with respect to time. Never. But just try these cases. Just do something in this condition so that the magnetic field is going to change. Then you will find any current in any deflection in galvanometer, and deflection in galvanometer means that the conductor current is passing through the conductor. So you are not simply going to find that in just vice versa of the Oersted experiment. You have to do some external work according to the conservation law of energy. If you are going to find some energy, you have to invest some energy. So this is the situation where you are moving the bar magnet, then you are doing some work, and your work is converting into energy, and you are going to find it in the electric current. So the whole experiment is saying that if you are going to find any current in a conductor with the help of magnetic field, you will have to ensure that magnetic field is changing, not only increasing, not decreasing. If you are increasing the magnetic field or decreasing the magnetic field, in both conditions you are going to get a current, but the direction of current is going to be different. So this we will talk about later about the direction of the currents. Now we are just focusing on the main part. What are the physical things we are going to do in this? So the physical thing is that you are constantly trying to change the magnetic field in the coil. So here comes with some conclusions. Conclusion number 1. If magnetic field around a circuit or conductor, around a conductor should be closed circuit. Conductor should be a part of closed circuit, not normal wire. You are not going to get this. So if magnetic field around a conductor is variable or changing, then induced current is going to flow in the circuit. Okay? So Michael Faraday was the first person who discovered this phenomenon. Okay? Second thing, according to law of conservation of energy, the work done in order to change the magnetic field is going to convert in the form of induced electric energy or current. Why the word induce is coming various times? These currents are not the real currents, okay? In which this current, this incidence is called magnetic induction, just because the bar magnet is not going to transfer some electricity to the coil. Bar magnet is inducing the coil with some conditions to flow the current.